Hey everybody, it's Mr. Piercy, and what we're going to be looking at in this lesson is how to determine the lengths of certain segments of chords. Specifically, we're going to be looking at uh, chords and secant segments, particularly with some tangents thrown into the mix also. Well, what we're going to be studying here is the relationship between segments inside of a circle. While they may not appear to directly have a connection between, well, I have this chord that's a certain length and I have this other chord that's a certain length, while it may not appear at first that there is a relationship between the lengths and different segments of a chord or different segments of, you know, chords or secants of a circle, there actually is. It's really hard to demonstrate. I really did try making some demonstration videos, but I couldn't quite get it to work out properly on the demonstration, so I'm not going to bother posting those. But uh, here, make sure you get the definitions copied down, get the diagrams added to your notes as needed. And the first one that we're going to be taking a look at is this one here, the segments of chords in a circle. So like I said, it doesn't seem intuitively like there would be a relationship between how long one chord in a circle is and the length of another chord in a circle, but there really is. And what we're seeing is that here, we're noticing is that if I take one segment of a chord, multiply it to the other segment of the same chord, it will equal the other two segments of the chord that it intersects when I multiply those together. And that is one of the first properties that we're going to be looking at as far as the lengths of segments of circles. Now, taking a look at what we're going to see here, we are going to have a little bit of algebra associated with this because, you know, that it is high school math. This is going to be the things that we're doing all year long. But let's take a look at the example that we see here. We have two chords, segment LM and segment JK, and because they're intersecting inside of the circle, the rule that we just saw on the previous slide, that says, well, the two segments that are formed when the chords are intersecting, the products of those two segments have to be equal to each other. So we're starting it off here saying that NK and NJ multiplied together, those products have to equal the other two segments multiplied together, which would be segment NL and segment NM. Substituting gives us x times x plus 5 for the product of the chords on the left side of the equal sign. Substituting on the right side of the equal sign is going to give us x plus 3 and x plus 1. Well, distribute to get rid of the parentheses. On the left side, distribute the x into parentheses. We get x squared plus 5x. On the right side, when I distribute, probably your algebra teachers called it foiling. We would wind up with x squared plus 4x plus 3. Because all we're going to do is, you know, your algebra teachers, like I said, they probably called this the FOIL method because we're going to take the first term, multiply it to the first term of the other one, and the outer terms together, then the inner terms, and then the outer terms, and then we combine the like terms that wind up being in the middle. Now, here, when I'm going to solve for x, and this is what you may or may not, you know, we might have a little bit of algebra difficulty here. Let me just go ahead and work the rest of this part out here because they're skipping a little bit of a step here that I think some of us may need to see. So we have x squared plus 5x is equal to x squared plus 4x plus 3. Well, let's say I want to take the x squared that's on the left side and move it to the right side. What we're going to see is that those two things completely cancel each other out. X squared minus x squared gives me a 0. And now I'm going to move down and I'm going to have 5x is equal to 4x plus 3. Moving the 4x over from the right side to the left side gives me x to be equal to 3. And that's kind of the step that they're skipping. They're skipping a couple of steps here, but that's how we're getting the 3 for the value of x. Well, we want to know what are the lengths of segment ML and JK. So when I substitute those back into their respective problems, or to the respective expressions, I should say, not problems. Well, ML is made up of its two segments, MN and ln. So we take the expressions that they have, substitute the 3 that we got, and combine all like terms. Doing the same thing for jk, we're going to say x is equal to, or jk is equal to x plus 5, substituting the 3 in for there, gives us the length of 11. Now, we're not saying that the chords themselves are congruent to each other. We're not saying that at all. We're saying that the products of the segments made of that make up the chords, the product of those are equal to each other. And that's how we're able to determine the length of the chords inside of the circle. So moving on, now we're going to be taking a look at segments that are not necessarily going to be contained inside of the circle. We have secant parts here, where I have an external part of the segment and an internal part of the segment. Well, the property that we're seeing here is if I'm going to take, I can take the external part here, EA. Ooh, let me turn my pen back on. I can take the external part and multiply it by its whole segment, and it will equal, the product of that will equal the other external part multiplied by its entire segment. So kind of similar to what we just saw, although now we have to keep into account we're not just multiplying one part to another part, I'm multiplying a part to a whole. And that's how we're setting up our equations in this case. Taking a look at the example that we see here, we're looking at segment RQ being the external part of secant RP. So I'm going to take the external part, multiply it by the whole thing. So that's why here we're saying RQ multiplied by RP, the external part multiplied by the whole segment. Same thing with the other segment. We're going to say RS multiplied by RT. Substituting the expressions that are given in the diagram, we're going to wind up with this. Simplify your like terms inside of the parentheses on the left side, and we're going to get 10. Multiply the 10 by the 6 on the outside of the parentheses, and we'll get a 60. Distribute the 5 into the parentheses on the right side, and we're going to get 5x plus 25. Move the 25 over through subtraction, then divide by 5. There we go, and we'll get x to equal 7. So in this case, we're not being asked to find the lengths of the secants. We're only being asked to find the value of x. But if I wanted to find the length of the secants, again, I would, like we did on the last example, just substitute the 7 in for the x, and then we could find the length of the overall second secant, which would be RT. So now that you've seen a couple of examples of how these relationships of the lengths of segments of a circle are going to be used, go ahead and pause the video and try answering these 2 questions. And when you're done, hit play again to compare your answers with how mine look. All right, hopefully we have a couple of good answers here. Let's see how you did. The way I'm going to set this up is for problem 1 is we're going to take the 2 segments of the chords and take the products of those segments and set them equal to each other. So for 1, I'm going to say x times 6 is equal to 5 times 12, and we're going to get 6x is equal to 60, so x is 10. For the next one, we're going to say the external part multiplied by the whole thing. So we're going to have one that says 6 times 14, because that's what 6 and 8 added together are. And then we're going to have another one that says 7 times x plus 7. And when we solve for that one, we get a 5. Now, the last one that we're going to look at here is really, really similar to the second one that we looked at, where we take the external part and multiply it by the entire segment. Well, in this case, segment EA, capital, well, the external segment EA, in this case, the one that's tangent to the circle, it is the external segment and it is the entire segment at the same time. So if I multiply the external segment, EA, times the entire segment, EA, well, we're just multiplying the same thing by itself, so that's why we're saying EA squared, or whatever points that we have for it. So EA squared will be equal to the external segment, or the product of the external segment and the entire secant for the other part, or for the other secant. So that's how we're getting EA squared is equal to EC multiplied by ED. Now taking a look at this one here, if you notice over here on the left side of the board is an old friend from Algebra 1 called the quadratic formula. Sometimes you can solve a problem, a quadratic equation. Sometimes you can solve it by factoring. Sometimes you can't. And that's what we're going to see something like that generated here. Now in other lessons in this unit, we've seen quadratic equations where we had to solve them by factoring. The example that we're going to be provided here, unfortunately, we're not able to do that. So setting up the example that we see here, RQ is the external part and the whole thing. So we're going to say RQ squared is going to be equal to RS times RT. Now substituting the values that were provided in the diagram is we're going to get 14 squared is equal to X times X plus 12. So square the 14 on the left side and distribute the X on the right side, and we're going to wind up with 196 is equal to X squared plus 12X. Now you can recognize, because I have an X squared, that we're having a quadratic equation of some kind. We're doing something quadratic. Usually when I have something X squared, that means that we're going to have two solutions. Now, the reason why I know that I'm going to have to set this up as a quadratic equation, or as a, what we would normally refer to in algebra is, we would say 0 is equal to ax squared plus bx plus c. The reason why I know I'm going to have to kind of turn the math that I have right now into that standard form of a quadratic equation is because I have an x squared on the right side of the equal sign, but nothing at all x on the left side of the equal sign. So we're going to take the 196 from the left side, move it to the right side, and we're going to wind up with this. Now, here, maybe your algebra teachers taught you how to determine whether something can be solved by factoring or not. In this case, we can't, and I'll tell you why we can't at the appropriate time. But what you see moving down, now here I'm not filling in any of the blanks because I don't think that they're giving nearly enough space to show the work properly. So I'm going to do my work here on the left side. Now here, the values that we see in the quadratic equation, or the quadratic formula I should say, has a b, an a, and a c as part of the values that we have to substitute. Well, the b, the a, and the c come from the standard form of a quadratic equation, which, so whatever number's here is a, whatever number here we substitute for b, whatever number's here we substitute for c. So keeping that in mind, I'm going to substitute the 12 where I see the b's, the 1, there's a 1 in front of the x squared, so I substitute that for a, and the negative 196 for c. Now we're going to start simplifying things. According to our order of operations, we have to do things inside the parentheses first. Well, everything that we see here underneath the square root, that's called the radicand. Radicand, D-A-N-D. Okay? We're going to treat everything underneath the square root pretty much the same thing that we would anything inside of the parentheses. We're going to simplify all of that stuff first. That's what the order of operations is going to tell me to do. So that's what I'm going to do. I'm going to square the 12, and I'm going to multiply the 4, the 1, and the 196 together, and we wind up with 144 plus 784. Moving on, simplifying now, we have like terms underneath the radical. We're going to combine those, and we're going to get 928. Now at this point here, I want to go ahead and tell you why we could not solve this by factoring. In the quadratic formula, we have underneath the radical, turn my pen back on, we have this that says b squared minus 4 times a times c. This is called the discriminant. If that discriminant works out to be a whole number when I take the square root of it, then I am going to be able to solve the problem by factoring. The problem is that there's a lot more numbers that I could have. There's a lot more values of a discriminant that I could have in a quadratic equation that do not give me perfect squares. So because the square root of 928 is not going to give me a whole number, I have to simplify the square root of 928. So 928, if you typed it in your calculator, doesn't give you, like I said, doesn't give you a whole number. So 928 is not a perfect square. The way that we're going to simplify that is by finding the largest perfect square factor of 928 and simplifying it that way. So that's why I've separated the 928 underneath the radical to be the factors of 16 and 58. Because 16 is a perfect square, and it's the biggest perfect square that is also a factor of 928. Now I take the square root of the 16, and I wind up with 12, or negative 12, plus or minus 4 times the square root of 58. Now at this point, we haven't done anything with the 12 or the 2 in the denominator. And the reason why is because our order of operations says we cannot add or subtract until I take care of all this stuff inside the parentheses. So at this point, like I said, the stuff underneath the square root, the radicand, we have to treat that like it's all in parentheses. So that gets done first according to our order of operations. Well, now we're done. We can't do anything else with the radical. So now it's at the point where we can add or subtract, multiply, or divide. Now, again, we have in the numerator 12, a negative 12 plus or minus the square root of 4 times the square root of 58. We're not going to try and add those numbers together in the numerator for two reasons. One, first and foremost, is that they're not like terms. Negative 12 is just negative 12. It's just an integer. Well, 4 has the radical 58. If you type that on your calculator, will give you a decimal number. It will simplify to be a certain value. Okay, but right now we're treating it as we can think of it as the same thing as 4x. We wouldn't say negative 12 plus 4x and then say, well, that's negative 8x, because they're not like terms. And it violates our order of operations. We have to multiply the 4 and the radical 58 before I could add the 12 to it. But we do have a 2 in the denominator. That would be considered a common denominator to both the 12 and the 4 of the numerator. So since I've simplified everything that I possibly can in the numerator, now at this point, it is okay to simplify the 2 to the 12 and to the 4 above it. So that simplifies to be negative 6 plus or minus 2 radical 58. At this point, we're going to separate it into two equations because, and again, let me just give you another quick kind of an algebra lesson. Here, whenever I take the square root of something, this is called an index number. If I have an index number that is even, I will get a positive and a negative answer. And the reason why is I can take a positive number and square it and get something. I can also take the other side. I can take negative of that number and square it and get the same value. So if I take the square root of the 25, I should be able to go back to whatever produced it in the first place, which I could produce a 25 by squaring a positive 5 or a negative 5. So that's why technically every time we take the square root of a value, because in the square root, even though we don't write it, it has an index number of 2 there. So I'd have to say I could get the positive or the negative value of whatever that number is that I'm taking the square root of. Now at this point here, we've simplified it where I'm going back to the quadratic equation now. So we've simplified it to have negative 6 plus or minus 2 radical 58. Now we separated it into two separate answers. Negative 6 plus 2 radical 58, negative 6 minus 2 radical 58. Now, for us in a geometry classroom, we really only care about the positive answers because, we can't have a side length that's negative. If I gave you this problem in an algebra setting, both of the answers are necessary. The reason why we have two answers is because of this. The largest exponent number in an equation, or in what we would call a polynomial in math, The largest exponent tells us, well, that's how many answers that there are. Because the largest exponent in this case is 2, there has to be 2 values for x that would satisfy the equation. If the largest exponent was 3, there would have to be 3 values of x that would satisfy the equation, and so on. So here at this point, this is where we're going to kind of let ourselves know, well, what are the decimal values? So -6 plus 2 radical 58 gives me a positive about 9.2, and the other one gives me about a negative 21.2. So again, here, these are considered the solutions to the equation, to the quadratic equation that we got. For us, in geometry, we want the positive numbers only. If we were in an algebra classroom, you'd have to give me both the positive and the negative answers. So in that case, I know it's kind of, I went off on a long explanation, but I'm hoping that it's helpful for you to understand, well, first of all, what the quadratic formula is, how it's used, why we simplify it the way we do, how we simplify the radical if it's not a perfect square, and you know why it has the plus minus in the equation itself in the first place. Hopefully that made sense to you guys. If not, please let me know, and I'll try to explain it individually if you need to. All right, so now that I've gone through all of that, you guys pause the video here and try working this one out on your own. All right, ladies and gentlemen, I hope we have a good answer here, and so let's see how it goes. Find the value of x, so that way we can find out what jk is. Let's see, where did I put my work? There's my work. So we started off by saying the external segment multiplied by the whole thing. So we set this one up to be jm squared is going to equal to jk times jl. Substituting the values, we get 64, or 8 squared is equal to x plus 6. Simplify the expressions, distribute on the right, square on the left, and we wind up with another scenario where we have to use the quadratic formula. Put it in standard form, meaning we get 0 on one side, whether it's on the left side or the right side really doesn't matter. We would rather have x squared to be a positive number rather than a negative number, so that's why I'm keeping it on the right side of the equal sign. And now we're going to have to use a quadratic formula, substitute it, simplify it, recognize that the square root of 292 is not a perfect square, so the largest perfect square of 292 is number 4, and that's how I'm getting -6 plus or minus 2 radical 73. At this point, we've simplified the quadratic in the numerator as much as it can possibly simplify. Now I can simplify the 2 in the denominator with the integers in the numerator, and then that's where the -3 plus minus radical 73 comes from. Separate it into 2 distinct values, and I don't think I mentioned it on the last example. These here are what we would refer to as the exact answers, and the decimal numbers would be what we would refer to as the approximate answers. So hopefully we did okay on that one. All right, so now here they're trying to give us kind of a real world example. We're trying to figure out, well, what would be find the distance from C to A, from you to from where you're standing to your friend on the opposite side of this fountain here. So the 105 CD, that is a tangent segment. So based on what we saw in the last example, we're going to say CD squared will equal CB times CA. And so when we take that information into account, we set up the equation like this. Substituting the values that we have in this case, we're going to say CB is 45, CD is 105. So we say 45 is equal to CA times 105 squared. Simplify, and I'm going to get 45 times CA is equal to 11,025. Then divide by 45, and we can say that the distance that the two friends are away from each other is 245 feet. So here's a very similar example, but instead of asking you to solve for the distance from C to A, it actually wants to know what the radius is. Now I know we know the distance from C to A, So that means we can get the distance from A to B and then take the radius that way. Okay, but that's not how I want you to work this problem out. I want you to work it out start to finish the same way that we did the first one to try and solve for the value of r. Okay, so don't just take the answer that we did from the last example and use that to answer this question, because you will have other questions like this where you won't already know what the length of a segment is. So you have to know how to set up the equation. So please try working this one out now, and when you're done, come back and see how I set up and worked out the problem. Okay, now we're going to set this one up pretty much the exact same way that we did the last one. I'm going to say CB times the whole thing CA is equal to this tangent segment squared. Now in this case, because CA is made up of the two segments that make up the radius, or the two radii that we see that make up the diameter, instead of just leaving it as CA, I'm calling it 45 plus the two radii that make up the diameter of the circle. So simplifying inside of the parentheses, that's going to give us 45 plus 2r. Now I'm going to distribute the 45 and solve for r that way. Okay. Now you could have easily figured out that the fact that the radius was 100 feet in this case by using the answer that we had from the previous example. But I really need to make sure that you guys can set up and solve the problem this way, because you're going to have other problems in on your assignments that ask you to do this where you don't already know the length of the segment. So that's it for this lesson. I hope the quadratic stuff didn't blow you off too much or be too much of a challenge for you. But again, just to kind of recap, we're looking at how the lengths of different segments compare to each other by taking various products and setting them equal to each other. And they're different for chords and secant segments and with tangent segments. But if you have any questions about anything you've seen in this lesson, by all means, email me, send me a comment, let me know what those questions are, and I'll be happy to help you with anything that you have. Until next time, ladies and gentlemen, thanks for watching and take care.